And really, what I want to convey to you today, if there's one thing that you could take away here, it's that if you're willing to put in some effort, I personally think that this is a fairly inexpensive alternative to getting more labor in your shop. It's not without a little bit of work on your part, and there is a learning curve to it. But to me, the realization I've had over the past several months is there's a pretty big difference between lights out automation, like being able to press the button and walk away for 24 hours and come back. We're still working on that, but there's a big difference between that type of automation and what we'll talk about today, which is automating some regular tending processes that just get you a lot more free time and keep you from having to babysit the machine tool all day long. And I've noticed that with our employees too, who have made parts using the ZA6 in the mill. Their reaction to this has been like, wow, this is fantastic. And that's kind of why we're here today to talk about this. So some backstory here. We developed the robot quite a while ago, and we kind of released it into the wild. We had some people doing welding with it. We had a lot of people doing robotics research with it because it natively runs on this open source code base called ROS. We had some people doing camera, film, and video work with it, but we didn't have a lot of folks doing machine tending. And a lot of that I thought had to do with the fact that, you know, the 1100 is a great prototyping machine. It's not really a production-oriented machine. And so if you really were a production-oriented person, perhaps the solutions Tormach offers weren't your cup of tea. But a few months ago, we needed to make just a ton of work pieces. So these are the little guys that we were making, and they're for an R&D project that we have going on. And we had a lot of them, 160 of them to complete out of steel blanks. And we just didn't want to load them by hand. And we thought, well, at some point in time, we should try doing some of the work with the robot that we've developed by eating our own dog food and using this ourselves. And to be honest, I was just surprised at how well it went and how easy it was to get this going. And as it turns out, the hard part was not the stuff that I thought would be hard. Getting the robot to pick the part up and move it into the milling machine's enclosure and place it in a vise, that was incredibly easy. It took like 20 minutes of programming a few waypoints, and then we were off to the races. The harder part was process reliability. Making sure every step is just bulletproof and 100% reliable turned out to be the challenge. So I think of machine tending as a problem that's kind of like warding off death by 1,000 paper cuts. So some education here. If you haven't thought about machine tending with a robot in general, I try to break the problem down into 3 different approaches. And the first approach that I'm going to list here, and the one that we took with the video that you saw as the teaser for the webinar, and the approach that we took for changing these parts out, was exchanging raw stock for finished parts. So that's using a gripper on the robot to grab a raw workpiece, moving it into the mill and dropping it off in a pneumatic vise. And there are some advantages of this approach. One is it's fast. There's not a lot of preparation required. You know, you might have to clean the workpieces up and deburr them, and you have to set them out in some kind of grid or array. But otherwise, it doesn't take a lot of effort on the operator's part to get this going. A disadvantage to this approach is the shape of the workpiece and the shape of the finished part needs to be conducive to being picked up by the robot's gripper, and needs to be conducive to being fixtured in a vise or with, for instance, a vacuum hold down system, right? Now you can obviously design different gripper fingers for different oddly shaped parts, but there's kind of more mental energy that gets put into that. So one disadvantage of exchanging workpieces for finished parts is if the shape isn't a nice, you know, deck of playing cards kind of shape, it can be tricky to find a way to hold them. And it can be tricky to find a way to pick them up. Another disadvantage is that you need a new or newish robot program for every part that you're making. That might just be something you assumed you needed. When we get to another method of tending a machine tool, I'll show you something where you don't, where it's just one robot program fits all. But for this, we had two different length parts that we were making, and it's kind of the same family of parts. You can see we have long ones and we have short ones here, and these two, we used almost the same robot program for the two, but the couple of the waypoints needed to be retrained for the longer ones, and so that's another disadvantage. You need a new program for the robot for every part, or a couple of modifications for parts that are in the same family. So another method of tending a machine tool with a robot is exchanging the fixture that holds the actual workpiece. And so what you see here is like a little aluminum mini pallet with two 0-point fixture knobs on it. So these are Shunk products. These 0-point, this is a ROS knob and a mini ROS knob. And in this setup, the robot's grabbing the smaller knob with a Shunk gripper, and it's moving the pallet over to a machine tool, and the machine tool's got a ROS system that grabs that 0-point fixture. And the big upside of this is it's really easy. Once you've trained the robot to do it, it doesn't matter what part you attach to that little pallet, right? The robot just has the same program. In fact, we could probably offer a solution for our customers where that program comes preloaded into the robot and it just kind of works, right? However, there are some downsides. One obvious downside is the robot can only carry 6 kilograms or 13 pounds, right? And so if you have a 2-pound fixture, you're reducing the weight of the total workpiece that you can carry. So that's one limitation. But to me, the bigger limitation here is that you have to pre-fixture the work to that little pallet, right? And so you've got to do some work on your workpiece, whether it's adding drilled and tapped holes to hold it down, or whether it's using toe clamps and attaching them all. There's some effort on the operator side to prepare your workpiece for machine tending. I personally think that if you have a long sequence, like if your machining sequence takes half an hour or an hour, then this might be great. And it might be great for a lights out setup, right? But if your machining sequence only takes 5 minutes, you don't want to take 1.5 minutes fixturing your part to these little pallets. It just doesn't make sense. And what we're talking about today is not 24-hour lights out automation. We're just talking about automating some stuff that would allow you to be doing other stuff in your shop while the robot is moving stuff in and out of the machine tool. So I think this is a pretty good solution. It's just not one that we're going to talk about today, because if it takes you an hour to machine your part, you already have an hour of free time to do other stuff in your shop, and maybe you're less inclined to automate this. And if you have any questions about any of this, just go ahead and type them in chat and I could just answer them in line here. So the third method of tending a machine tool, when I break this down into these 3 methods, right? The first one is just taking raw stock and putting in a vise, pulling out the finished part. Second method is prefixturing your workpiece to a small pallet and moving that pallet in and out. And then this third one is kind of a hybrid. And I don't know of other companies offering this, but there's a company called VersaBuilt, and they make a system called multi-grip. And it's a vise that has a set of soft jaws, and the robot gripper actually removes the soft jaws from the vise. And we've got a couple of videos on this, and VersaBuilt has a whole website showing this off. But essentially, it's a method of exchanging soft jaws. And that's kind of nice. One of the big advantages here is most machinists know how to make soft jaws. So even if you don't know how to make a gripper, you probably know how to make soft jaws. You don't need to worry about the gripper design. You just make soft jaws, and those things open and close to hold your part. Another big advantage of the multi-grip products is part flipping is very easy. You've got one set of soft jaws. If you have 2 vices, one set of soft jaws and another set, and you grab your part, you can just flip it over using the soft jaws themselves. So part flip is really easy to handle with the multi-grip system. One of the disadvantages, though, is that the orientation of the system and the product is such that you really can't come in through the side window of the milling machine. You've got to have the robot coming in through the front of the milling machine. And to be honest, we got 2 doors on the 1100 and 770 MX enclosures. a little more challenging to automate. And then also, I suspect if most of you are like I am, I want to be able to use the milling machine without a robot occupying the front space of it. I'd like to be able to use it both with a robot and without a robot. And right now, training the zero location for that multi-grip, it's a little bit of a challenge. Once you get it done, you want to have it set up for a while. We're working on making that easier, but this is not as flexible of a solution. It doesn't allow you to use the mill as a normal mill when it's not being an automated mill, if that makes sense. So the rest of this presentation, I'm going to focus on that first method that I described, taking a raw piece of material from a pick area, moving it into the machine, dropping it off with a pneumatic vise, right? Number 2 and 3 are great methods. I don't mean to disparage them. The drawbacks there are that on the pallet system, you kind of only really conducive to work pieces that take a long time to machine. And if you have something that takes an hour to machine, you already have some free time. And this multi-grip system is fantastic too. But until we get a better way, either using vision or force feedback to train that multi-grip vise position, I feel like rolling the robot in front of the mill and leaving it set up there really hinders people from using the mill as they normally would without a robot. Okay, any questions so far? Part flipping. We have a part flipping question from Josh. I mentioned part flipping. How challenging is chip clearing, making sure the part's all the way down in the fixture for the second op? I will hit that in another couple of slides, Josh. Thank you very much. So moving on to pick area strategies. So in the video and what you see in this photo here, or you see behind me as well, we settled on using a grid, a 2D array of parts. We actually started off with a ramp. I wanted to make things just brain dead easy for us. And so we made it just out of MDF, gravity fed ramp, and the parts lined up all in a row. And when you grabbed one from the end of it, the whole stack would slide down and another one would show up. And that was kind of nice because the robot programming was dead simple. One waypoint for the pick spot, right? And then the new part just showed up. The downside was this grid has 30 parts on it. That ramp would have had to have been pretty long to get 30 parts. There are some other methods of doing this. You can see on our grid, we're just using a fixture plate with some dowel pins in it. And that's kind of nice because it allows you to have big work pieces with a fairly wide spacing, or smaller work pieces with a tighter spacing. And so you can kind of change the density of the parts that you lay out on the grid. The robot programming is not that hard to do an XY array, and we'll share code and help people out with all that. It's I won't say trivial, but it's fairly easy. With this grid, I don't know if it's visible in this photograph, but we actually tilted the grid up at a slight angle. So it's like at a 15-degree slope, which was just enough for gravity to kind of keep the work pieces in place, which is nice. An alternate to a fixture plate with dowel pins that's modular is just to do something like I'm showing here in this photograph. This is a company that's not far from us that we're friendly with. They just milled an aluminum plate and they milled little shallow pockets out for each one of their work pieces. And actually, they made this plate to fit a family of work pieces. And so you can see in this empty pocket that's in the front, you can see multiple different sizes that they can manage. So this entire pick area that they did, they custom machined, and it fits 1, 2, 3, 4 different parts all in a similar family. And it can do a nice 4x5 array of 20 of them. And you can see they've got slots milled into the thing for their gripper fingers, which are grabbing the parts on the diagonal. An alternative that we didn't pursue was doing like a gravity-fed stack with a pneumatic pusher at the bottom. This has got a lot of advantages. It's very compact. You can fit a lot of stuff in there. It's really easy to load more in. You can load more in while the robot's doing other stuff. The downside is you kind of have to design that stack feeder for each workpiece that you're doing. It's very particular to a workpiece size. So we talked about prototyping one of these. I have a friend about an hour away with a woodworking company that uses these stack feeders all the time in his business. But they're just so custom for each different workpiece size that it didn't feel like a great solution. Richard asks in chat, just to confirm, it looks like the right-hand side is the optimal location for the robot. I personally think the right-hand side is the optimal location. The ATC, if you have one, makes the left-hand side a little less optimal because you got to get in under the ATC, and there's not a ton of clearance, and most pneumatic vices are a little higher. You know, you've seen like the mod vices that fit very low to the table. You're not going to find a pneumatic vice that works that way. And so right-hand side is my preference, and I really like it because if you're like me, you probably want the ability to use the mill manually yourself. So not parking the robot right in front of the mill has a big advantage in that you can automate some stuff or do one-offs without really mucking around. So I'm a fan of the right-hand side. Okay. So I hinted at this earlier, but the big learning, the takeaway from me was the challenging part of automating a milling machine with a robot is not picking up the part and putting it in the vise. Like really, that was 20 minutes of programming. Maybe add another half an hour of programming for the grid once we got the grid set up. The real challenge here is process reliability. And if you imagine the steps that a machinist takes when you're loading a part into the machine, right? You're typically taking a look at the workpiece, you're making sure there's no chips or anything on it. You're going to clean off your vise jaws if you're using a vise. You're going to set that workpiece down in there. You might bump it up against a work stop. You're going to close the vise to a specific pressure. You may use a dead blow hammer to kind of seat the vise or make sure the movable jaw hasn't lifted. You're going to close the enclosure. You're going to kind of visually inspect the area before pressing cycle start. And if you've pressed cycle start once before, you probably know that the program's going to run fine. You press cycle start again, and you can walk away. But there's a lot that goes on when a human being is doing that we need to repeat with the robot, right? And so that's one of the things that makes this challenging. And I'm going to start with each one of these steps, right? So the first step logically in this process might be picking up the raw stock. We actually did not have any picking failures here. The parts start out clean. We deburred them. We put them in the right location. This kind of just works. It's not rocket science. This was a very reliable step in the process here. We made a couple of little modifications. Even though we had not had a pick failure, we decided instead of lifting straight up from the pegs as we had started, we modified the code just slightly to kind of lift at a diagonal away from the pegs so that the part doesn't rub on the pegs. We hadn't had a failure from that, but we noticed, you know, opportunity for a failure here. But in general, picking a workpiece from a table is fairly easy. We always double checked though. So the next thing we would do right after picking the workpiece is we'd bring it over to a proc sensor and you'd be able to see whether you did it correctly or not, right? And so placing the workpiece was a little bit more error prone. We never had a problem placing the workpiece in the correct spot. The robot's super repeatable. The tolerances here on this vise, it opens, you know, tens of millimeters, and we milled some soft jaw pockets for the gripper fingers, and the accuracy required to stick the thing in the right location is no problem whatsoever. The robot's got fantastic repeatability. So getting it into the right spot was not a problem. The issues that we did have had to do with not getting the vise jaws washed correctly, and also with a burr on the workpiece interfering with that bump up against the work stop. So I'll describe this here. What you saw here was us blowing off the finished part with an air knife. That's the black thing in between the two grippers. And then we blow off the vise jaws again with that air knife. And we're bringing this down and we're dropping that workpiece off. And then we move and we actually use the opening of the pneumatic gripper there to bump that workpiece up against the work stop. And I don't know if you could see it, but the vise opens and closes twice. And we do that just to settle the workpiece in the right location. And then I mentioned that we check the workpiece when we pick it up. We also check it when we pick up the finished part and we bring it over to the proc sensor there. And you know, I mentioned process reliability being the name of the game. Anytime you can check to make sure something happened correctly, it's good to do that. If you think about it, and I don't, you know, a lot of engineers probably in this room, if you have 15 steps in a process and each step is 99% reliable, you might think, oh, 99%, that's pretty good, right? But the odds of successfully completing a sequence of 15 steps where each is 99% reliable, the odds are 1 minus 99 to 0.99 to the 15th power. It's only 86% chance that you're going to complete this reliably. And we want to complete it reliably 100%, right? And so you really need to make sure every single step is 100% reliable to combat that 1,000 paper cuts that I was talking about here. So this was the placing, and we did have a couple of failures out of 160 parts. One was a result of a burr on the edge of the workpiece, and when this guy nudges the workpiece up against the work stop, that burr on that workpiece was such that it just caused the back edge to lift a little bit as we were nudging it up. So we had one failure related to that. We solved that by just deburring all the workpieces. We didn't see that failure again. We also had two parts that were off in their thickness by 10 to 20 thou, and we're certain that that was caused by a chip and trapped under that vice jaw surface. And if I were to do this again, I would take the time to use the mill's coolant to thoroughly wash the vice jaws before blowing off the vice jaws. You notice what we're relying on here is just the blow off sequence to clean the vice jaws. You see we grab the part here. You can actually see the mill doing a tool change at the same time. So Richard, you asked earlier about the connection between PathPilot and the robot. That tool change wasn't part of the mill's program. That tool change was just the robot sending an MDI command to the mill because we wanted to kind of compress the cycle time by getting the mill ready for the next part. Anyway, if I were to do this over again, I'd use flood coolant to wash that off. One of the reasons we didn't do that to begin with is you can see we don't have an automated window. We're just relying on reduced pressure flood coolant to keep coolant and chips from going everywhere outside of the enclosure. And we have a half window that's put there. I'll talk about what we're doing there with some future accessories in a little bit. All right, so that covers placing. Removing the finished part, you saw the wash down of the part, the blow off, removing. We didn't clean the part. If I were doing this again, I would clean the part, and you could clean it in a couple different ways. We could have had an air knife station somewhere still inside the enclosure that we used to blow it off. Or, and this is something I've seen a friend do that automates the guy with the mini pallet system. They actually dunk it in a bucket of water, which would have been a pretty neat way to do it. The pneumatics and the gripper are all waterproof. It wouldn't be an issue to dunk it in a bucket of water. We had steel workpieces, so that wouldn't have been great, but we could have used alcohol or something else. Ed asks, is the arm accurate enough to put a micro switch in the end of the jaw to confirm the part placement? Ed, do you mean the soft jaws on the vise, or do you mean the gripper jaws? Either way, I think the answer is yes. The robot's very, very repeatable. Robot accuracy and robot repeatability are two different concepts. The robot accuracy is very dependent on how well the robot's mastered and whether or not it's calibrated. And what we've found is that for most of our customers, accuracy is not as important as repeatability. Repeatability of this robot is unloaded repeatability is, down to the single-digit thousandths of an inch. And so you're plenty of accuracy for, I think, what you're describing. You could also use a proximity sensor embedded in the gripper design that would help out as well. So telling if a chip is under a part is an interesting one, and I'll talk about some other strategies as we get further in here. So we covered cleaning, and then of course we checked to make sure the finished part was actually in the jaws when removed here. So pitfalls. and this is exactly where we talk about chips under a part. So this is one of the issues. And you can see if you really squint your eyes and look at this, you can see some of these chips get quite small. I think the best approach to this is a full pressure flood coolant washdown of the vise followed by an air blast. If we had a wireless probe for the 1100 MX, I would also follow this up with a probe of the workpiece to make sure it's in the correct position. And I think with a probe of the workpiece, perhaps with a consistency of workpieces for this stock wouldn't be might have a hard time telling just an oversized workpiece from a chip. But I think our best strategy is try to eliminate any kind of chip under the part by making sure that the parts are all clean and that the vise jaws are thoroughly washed with a flood coolant bath and then blown off as well. Burr on workpieces we mentioned. Cleaning the workpiece after we remove it is something we didn't do. And so what I also noticed was we had to kind of clean the surface of that fixture plate as we loaded new stuff up, because you didn't want a little chip that came in from a finished part to be entrapped by the next load of parts that you brought in. So deburring the workpieces helped us out in this case. Might not be required in other cases if you don't have, if you're machining both edges of the part and you're not really bumping it up against a work stop, then you wouldn't really need to worry about the burr, I don't think. Another pitfall here is oddly shaped workpieces. So we talked about this a little bit. This is a really interesting research article done by a group up in Washington. And they used generative AI to design 3D printed gripper attachments to use passive grippers to grab oddly shaped items. And I just love that rabbit that they pick up. But this is just to illustrate that if you have a 3D printer and you're not shy about modeling something up in CAD and sending it to the 3D printer, you can get very creative with gripper design. Tony asks, yes, this is being recorded and will be available on demand later. Josh asks, probe on the robot. We actually do have a probing command on the robot, and we've got the ability to put the probe on the robot. And I kind of felt like the end effector was a little crowded with the air knife and the two pneumatic 2-finger grippers that we set up here. But you certainly could do a probe on the robot, and you'd have a pretty accurate CMM too. There's 23-bit absolute encoders on each of the joints of the robot, and so it would do a pretty good job of telling you exactly where stuff was. I think that might work. Ed, speaking of wireless probe, you would not know a guy that could get Tormach to implement that, would you? Yeah, it's something we're working on, and I will tell you also there's some decent aftermarket options that some of our customers have made too. We don't sell them on our website, but I know that other customers have talked highly about some of the probe offerings that are out there available for our equipment. And then the last one, Richard, Renishaw plus Tormach. Yeah, Renishaw is pricey, and so that is one of part of our value proposition is being capable and affordable. And Renishaw has been just a little bit out of that price range for us. On to more pitfalls. So wear on the tools was one we noticed. 160 of these work pieces, we needed to rotate the inserts on our face mill while doing this. And had I not been walking by the machine and noticed some sparks flying from the insert end mill, the face mill that we were using, I would have not remembered about tool wear, which is kind of interesting. You're not sitting there watching things as closely as you would be if you had to be tending the machine yourself. It's not just the mill tooling you have to think about. We had a little bit of wear on the gripper fingers. They're like little urethane pads, nothing that would have caused a problem, but it is the kind of thing where if you're doing this day in and day out, you get wear on gripper fingers. I know that the suction cup pneumatic grippers are specifically made with wear in mind, and you choose different suction cup types depending on whether you can pick up the thing you're picking up with a durable rubber versus a less durable material. Richard asks again, the interface of the robot pneumatic, the end effector is easily changed in process. Right now, we only have manual change end effectors. There are companies that do make automatically changeable end effector systems that have pneumatics running through them. We just haven't tried them. I don't think that if you had a compelling reason to do an end effector change in process, I don't think it would be that hard to do. The expense of that stuff is pretty high, and if we saw a need for it, or we had customers that wanted it, it'd be something. I'll put it this way, Richard, if you end up with a robot and this is super important to you, I could send you some references, or we could work with you to see how well those worked. I know several companies that do make end effectors that have the ability to automatically change and include pneumatics routed through them. We just don't offer them right now. Lastly, in the pitfalls category, every application is different, and I'm sure that we're going to find more of these paper cuts. And our goal is to kind of create a toolkit of solutions to these paper cuts. It's one of the reasons that we've been trying to get people to our user forums, is to post what they're doing and the challenges that they have and the problems, especially, so that we can fix them. If we don't know about the challenges that people are facing, we're less able to address them. So if this is something that interests you, we really, really encourage you to be vocal on the user forums, not only when things go right, but especially when things go wrong, because that information, weirdly, is more valuable to us than knowing about when things are going right. I know we're getting close to an hour mark here, and I want to leave some time for maybe audible Q&A. So I'll try to speed up through the last of these slides. Some tips. One might seem obvious in hindsight, but breaking the program, the robot program, down into individual tasks and writing subprograms for each task is a big advantage. So every single thing you saw in there, picking up from the grid, checking at the prox sensor, moving through the enclosure door, blowing off the vise, all of those were written as kind of separate programs, and then they were brought into the main program. And if you know any G code and you've written a G code subroutine, you're more than capable of writing a robot program and a robot function or subprogram. The programming language for the robot is Python. I'll talk about that in a second. It's just much, much easier than G code, easier to learn, easier to write. But I wrote each one of those little functions as a separate encapsulated program, and that did a couple of good things for me. One, I could test just that one little atomic step over and over and over again to make sure that things were going correctly. And so I mentioned lifting the workpiece away a little bit from the dowel pins to make sure it didn't rub. That was super easy to see if all I'm doing is picking something up and putting it down, picking it up, putting it down, picking it up, putting it down. And I could just run that operation 100 times, make sure everything was going to go well. So being able to write test cases for each one of these things is a lot easier if you kind of modularize your program into each little individual task. The other nice thing about writing a separate program for each task is that when I have to go automate the next part that we're going to make in here, I probably don't have to rewrite the stage where I move through the enclosure or the stage where I go check something against the prox sensor. It may be that a lot of the code I wrote for this is just reusable. So that's another good reason to write each one of these individual tasks as its own compartmentalized program. Another tip, just check everything. If you have an opportunity to check it, do it. I love the idea of putting a prox sensor or a micro switch out at the gripper jaws. We could do it that way. Verify the picks with the prox sensor, verify the places, verify tool links if you have a tool setter, the open door and closed door I'll show in some future work here. Verify all that. And then how you respond to those checks could verify. If you're in the shop and you're just going to be doing other stuff while this is happening, then maybe it's just a let me know, send me a text message or an email or make a sound, or it could just be just abort and I'll be in the next morning to fix it. I'll see how many pieces got made. Or it could be even try again. I tried to pick something up and station one, for whatever reason, the piece was missing. Let me just go to station 2. We haven't personally tried that last one. It's like kind of stage 2 automation, but there's no reason why it's not doable. Richard asked a bit about the robot to machine connection earlier on. I'll say it again here in case people missed it. The robot and the milling machine, if they're plugged into the same local area network, so like physical Ethernet cable plugged into a switch, plugged into your local area network, the robot just sees the milling machine. It shows up in the user interface as a connected device. Actually, we've got several milling machines in the shop here, and so the robot is kind of aware of all of them because they happen to be all in the same local area network. And you can send commands specifically to those machines. If there's only one machine, you could just send a command. If there are 2 or 3 machines, you name each machine in the setup tab, and then the commands can actually have the machine name in them as well. The robot can tell whether the machine is idle, meaning there's a program loaded, but it's not doing anything, tell them whether the machine's ready, tell them whether the machine is running, so we can check and wait on things. And then it can issue cycle start commands. It can issue individual NDI commands. You saw that when it was changing tools. The mill was changing tools and the robot was picking stuff. And in the future, we want to be able to add the ability to load individual programs from the milling machine's file system, have the robot decide whether to load different programs. It does work with wireless, Richard. I recommend a wired connection though. But it will work with wireless dongles. It's just, and you may say, well, hey, my mill controller doesn't have a wired connection because I only have one Ethernet jack on it and it's going to the mill control board. A little USB to Ethernet adapter works quite well. So that would be my recommendation, is not using Wi-Fi. It's just too much weirdness. And all that robot machine connection stuff is available in the robot programming language documentation up online. I talked a little bit about Python here. I'll try to keep going quickly. The robot's programming language is not G-code, it's Python, which if you don't know any Python might sound scary to you. If you know any Python, you're probably delighted by this. There aren't a lot that you actually need to know, and a lot of things you actually need to know here. You really, and we've got quick tip videos on these. Knowing waypoints and waypoint types is important. Knowing user frames, a user frame in robotics is kind of like a work offset in CNC land. That's important. Knowing tool frames is required if you're going to use 2 grippers on the same end effector, like you see us doing here. If you just use 1 gripper, you can actually skip knowing tool frames. And I used to say this when I taught CNC programming. You don't have to know how to write G-code to run a CNC machine, but it really helps if you can read G-code and modify G-code a little bit. Like if you post-process your G-code, it's really helpful if you can read through the first few lines and see what the post-processor has told your machine to do. It's the same here with Python. The robot's conversational screens will write the Python code for you, but it really helps to be able to read it and be able to modify it a little bit. And if you're the kind of person who can write a G-code subroutine, I can guarantee you can write a Python function. It's a very easy language. It's infinitely more popular than G-code. There are just a ton of great free tutorials online or on YouTube for Python. It's also a super flexible programming language. Robot stuff, I'll do this really quickly. We have quick tip videos on all this. We've got 2 different types of waypoints. Joint type waypoints are kind of like G53 absolute coordinates in milling machines. These guys do not get modified by an active user frame or work offset, right? So you could change user frames all you want, but a joint waypoint is always going to be exactly where the machine goes. I recommend using these for all non-precision locations, like a safe position above the pick tray or a safe position moving through the enclosure window, things that'll never change, right? Cartesian waypoints are kind of like normal XYZ coordinates in your milling machine. These do get affected by a user frame or a tool frame if those frames are active. So user frames, remember, kind of like a G54 or G55 offset. And so you want to use these for all the precision points. So when you see the robot placing stuff into the vice jaws, that's a Cartesian waypoint. The reason for that is if I kick the robot table and bump it over a couple inches, I want to be able to just retrain that user frame so that the above pick, the nudge, all those things are still valid, right? A couple different move types that we use here. Move J is a joint move. It's basically saying I'm going to move in whatever way I feel like moving from point A to point B. They're really easy to plan this move type. There are some configurations for the arm, right, where a linear move is impossible because, like, if we move through one of the link arms for the robot, it's not going to do that. It's not going to crash into itself. So a joint move would work for that. A linear move obviously wouldn't. So I recommend using move J whenever you don't need a move L. A move L we use whenever linear motion is required. So that 2-inch move you see when it picks something up, or the 1-inch move you see when it places something down, or the nudge move, those are all linear moves. Everything else in that sequence that you saw is a joint move. And we have a ton of robot example programs. These are kind of like programs that show how those two move types, or how user frames, or how pop-ups, or anything else work. All this stuff is up here in this robot programs GitHub thing. And I wonder if I can paste that in. No, Teams doesn't let me copy from a slide that I'm presenting on. That's too bad. I'll paste this into chat when we're done here in a little bit. But we've got this great library of programs that show how to use the various commands in the programming language. Future work, I kind of touched on this. So one of the things that we're doing, we've made a new side panel that would replace the right-hand side panel for the 1100 and 770 enclosures. And it includes a sliding window with an air cylinder up on top. The air cylinder will have sensors in it for open and close. We've got solenoid plates that are available now for the robot that would be able to communicate with this and command it. This should allow you to use full flood coolant pressure in the machine and trap everything and keep it from coming out. You can see there's kind of a little tray to catch drips when the window's open here that comes out. So that should be coming. We've got a prototype that should be here in December, and if it looks good, we'll go ahead and move into production. I expect to be able to sell those probably February or March. We're also working on this self-centering vise. These should be available for sale a little earlier, although we are working on a subplate here for this. So that should be available sooner, I'm guessing sometime January for the self-centering vise. And then we have a number of software improvements. So I mentioned collision modeling at the beginning of this. It works now. There's some clunkiness to it that I really want to improve for customers. But that collision modeling, I've got a couple screenshots here so you can see if you have a connected 770 or 1100, those machine models just show up. Right now, customers have to orient where the robot is relative to the machine. But the robot, if the machine is present in the collision scene, the robot will not collide with it. And we're just making some things easier, like attaching a custom end effector tool to make sure that while the robot doesn't collide with the enclosure, the tool doesn't collide with the enclosure either. So that should make it a little bit easier. There's another shot here, and it's cool. The mill is actually completely modeled in here. So if you have an MDI command that causes the mill to move, you get to see it show up and the robot is moving as well. A couple other software improvements. We're working on having an easier way for people to do text messaging or email notifications from the robot program. We've got some additional robot machine connection commands, like loading various programs from the Mills file system. And then the last, and this is probably off about 6 months, is we are working on visual recognition of work pieces. So the robot, instead of loading from a grid, being able to just see work pieces sitting on the table in front of it and grasp them, what's called unstructured grasping. All right, so I'm going to wrap this up here and take some questions. I wanted everybody here to know this is something that we're pretty committed to. I really think automation is going to be, I don't want to sound too sappy here, but I have this vision where you could walk into a 2-car garage somewhere in suburban America, and instead of seeing a minivan and the kids' bikes, you'd find like a Tormach mill and a robot or a lathe working together in kind of a lights out fashion. And I hope that over the next 10 years, what we can do is try to bring back cottage industry to the United States this way. And so that's something that we're pretty committed to. And what we're looking for are interested parties to help us out with this. There was a learning curve for me setting this up, and I know the robot pretty well. What we're trying to do is make that learning curve a lot less steep. And we can do some of that by making our software easy to use. We can do some of that by putting together better training aids. We can do some of that by helping other people put together YouTube videos showing it off. But we do need our customers' help, right? Because I'm not in the business of making hundreds of different parts every day. I'm not a job shop, and I don't get requests for stuff like this regularly. And so we're looking for people that are interested in walking down this road with us. If you're interested, I've got a link here to our pre-sales consultation form. Brian will toss it in the chat. That would be a time to talk with Davey or Stephen or me about robots and automation. What we can provide, and what we don't normally provide when you buy a milling machine from us, is applications engineering. But what we can provide in this instance is some additional applications advice. If you have questions specific to the thing that you're trying to make, we'll sit down with you and answer them, and we'll give you our guidance. We'll also, for people that are interested in walking down this road with us, we'll provide some additional training for you online, I guess in person, meaning over Zoom or Teams. We'll actually sit down and walk you through, answer questions, give you an idea of how we would go about doing this. So this is a little bit more hand-holding than we provide for our CNC machines. And what we would need for you is an open mind. There are problems you will encounter trying to implement what we just showed off here. We want to hear about those problems. So participation in our forums, talking to us about the stuff that was challenging so that we can make it less challenging for the next person that comes along. And so with that slide, that's kind of the end of our webinar here. If you guys have any other questions, so I see from Richard, will the door have a wiper or air knife? An air knife is something you could mount anywhere, so sure. The wiper is something that I believe we do have, although I would have to check with Jason. So that's a question I'll have to answer in a little bit. Are there any questions? And feel free to pop yourself off of mute and ask questions audibly if you want, or you can continue to type them in chat. But do we have any other questions here that I can answer for people today?
Does the Python eventually get turned into G code?
No, it actually gets just interpreted by our robot. The robot control interprets Python as its programming language. And the really neat thing about that is that it'll interpret any Python program. So you don't have to, it's not just limited to like the moveL and moveJ commands. If you could bring in any Python library and the robot will import it and run your Python code, even if it didn't tell the robot to move, it'll do that. And so I mentioned earlier that the multi-grip product was kind of tricky to train the 0 point of, and it's got this sequence of small moves to get it to engage and disengage. And when I was working with it a couple of years ago, I kept finding that it was like it would move in, it would move over, move up, and move down. I just couldn't tell where it was in the sequence to see what was going wrong. And so I brought in Google's text-to-speech library, and I just had the robot telling me what it was doing. And it was literally 3 lines of code to have it telling me, hey, I'm moving to the 0 position. I'm shifting over 3 millimeters. And the robot was talking. And that's one of the powers of using Python as the robot's programming language, is that you can bring in all these other Python libraries and use them like you would in any other Python program. So if you already know Python, and then that should probably excite you quite a bit. If you don't know Python, don't be intimidated. It truly is a much easier language than G code, and you don't need to know it to be able to do this stuff. It's helpful. It's something I would recommend. Any other questions? I'm sure someone's got a question.
So theoretically, could you have that go and interact with like website orders or something of that nature?
Oh yeah, yeah. In fact, and I think we have a video of this. Monty, didn't we do a video where we sent data up to a web server? No.
To a phone.
No, we had a video where we sent stuff on a text message. Yeah, but Richard, like, when I was doing some tests with the probe on the end of the robot and probing like a whole bunch of positions, and I was saving those positions off to a CSV file, which is, there's just a CSV library in Python that makes it really easy to write CSV files out. And so I was saving those probe positions out to a CSV file. And if you wanted to bring in the HTTP requests library, which is a Python library, and upload that CSV file to a website, it would be super easy to do that.
So if you wanted to use this robot for just in-process inspection, you could have it generate inspection reports.
Mm-hmm. Yep. Anything you could do with Python, you can do with this robot.
Now, you mentioned earlier that you haven't tested multi-machine, but what would be the hurdle, you think, communicating with two machines in one program?
I don't think there would be much of a hurdle at all. We just haven't, I mean, physically, I think there's more of an issue of physical than otherwise. And we get questions about the lathe too, but you know, if you're making something that's under an inch in diameter, then a bar puller and the collet closer is your solution for the lathe. And if you're making stuff that's larger, you'd need a pneumatic chuck for the lathe, and we don't sell one. But there's no reason that the robot couldn't, if you found the correct pneumatic chuck, you know, at the D14 mount for the 15L, there's no reason you couldn't have the robot automating a lathe for larger work pieces too. Physically, with the kind of my desire to come in through the enclosure, the right side of the enclosure, we just haven't had, I guess we could have two machines that were kind of front and back with a robot in between them. Just haven't gotten to that. I don't think it would be a problem at all. The robot's language makes it really easy to direct commands at any number of machines. The devil's in the details, though, which is why we're why we'd love to have some other folks, you know, being active participants here. John.
Hello. What sort of rigidity is required for mounting this unit to be able to maintain the accuracy?
That's a great question. The accuracy isn't so much going to be a function of the rigidity. What you will have happen with a flexible stand is you'll start to see the robot fight itself. So it's got a PID loop that it tunes. I mean, it's actually much more complicated than that, but imagine a PID loop tuned at each of the joints, right? And what you can have happen if you've got a heavy payload and a floppy stand is you start accelerating and the stand has some compliance and you end up with an oscillation, right, as the robot is trying to move something around. If you have a very rigid stand, and in our R&D facility, we've got an incredibly rigid welded base, you don't have any of those issues. If you have a floppy stand like this is just a steel table from Zorro here with no reinforcement. And like moving my laptop's camera, thinking that's going to change the view. This guy is stiff enough. I mean, it works fine for this application. We brought a similar setup to the ROSCON show, and we're using a pen to draw stuff, and the moves were very fine, and so it's moving around with the kind of drawing application. And we noticed that we had to tune stuff down quite a bit to get it to keep the stand from bouncing and causing inaccuracies, which is a long-winded way of saying really depends on your application. John, if you've got a drawing robot and you're using a pen to do a bunch of very fast type moves, you want something that's very, very rigid. If you're just moving work pieces in and out of a milling machine, a steel table would be adequate. No, you're still muted, John.
There we go. Would there be any way to recalibrate its own position in process? So, for example, if it shifts, you're talking about this oscillations and things like that. Would there be any way to recalibrate in process of where its location is? So if it knows it's moved 1/8 of an inch or something, that it could adjust for that. Is that something that might be possible?
You know, we haven't had that problem. I mean, like there are 4 hefty bolts that fasten the thing down, and so we have not encountered a situation like that. What we have encountered is a situation where the table itself has moved, right? Especially if you just have this one's on casters. We've got the casters lifted up off the ground, but we have had that situation. You could certainly recalibrate stuff in situation. It's just a matter of programming it. So my personal approach to that would be to fix the mechanical problem and not rely on a software recalibration. But I could imagine a routine if you had a touch probe mounted to the system where it just always probed the vise and reaffirmed its view of the world before placing the thing. That would be a doable.
Possibly probing something like the window location that it has to go through.
Yeah. Yeah, or one of the things we're working with now is a 3D depth camera. Intel makes one called the RealSense. Luxonis makes one called the Oak D. And those are cameras that can actually look, and they use stereoscopic vision. They return a point cloud with XYZ positions. And we're just now looking into using a 3D camera to verify the location of the milling machine's enclosure. I'm not sure that we're going to end up doing it. There are some technical challenges that sounds good on paper, and then you actually try to do it, makes it kind of less conducive. I personally think probably the best thing to do would be to have a table with an attachment piece of angle and the enclosure of the milling machine and some holes that are drilled. And as long as we're within a couple millimeters of where we need to be, great. And then we can spend time here at Tormach, you know, very closely verifying everything. And then customers, when they purchase that thing, would just choose from the drop down, hey, I bought this kit and here's where it is.
Great, thank you.
I'm being told that we're 3 minutes past, but I'm happy to take any other questions that people have. Or if you think of questions after this and you want to email me, you know, welcome to do so. If you send an email to my address, drogge@Tormach, or to info@tormach.com, be happy to answer any questions. Don't forget about the survey. We'd love it if you take it. We're going to give you a $25 gift card. Just fill it out if you can. That survey should be open till 1 o'clock today. Last opportunity for a question. Oh, here we go. In-house implementation of automation. So Ed, what do you mean by in-house? And as Ed is typing, I'll answer Lee's question. Yeah, I mean, a lot of the vision stuff starts with OpenCV, but maybe that's a much longer discussion. Oh, so what you're saying is, so Ed Cook comes to us and says, I want to do this, but I'm not sure it's going to work. Will you guys set it up and prove it out on our machine? Is that what you mean? We have steered away from that in the past with our equipment, because usually the number of tire kickers and the work that you go through for the tire kickers doesn't end up working out for us. But if you're already a customer of ours and you're seriously interested in it, we could have a chat about that. Especially because we're pretty interested in finding more examples of this for ourselves to go through. So yeah, go ahead and shoot me an email if you would. That'd be great. And Jose asks, if you have a step file of the custom-made gripper, is there a way of in PathPilot to model it? Yes, there is. And in fact, if you look at the GitHub example programs repository, which I didn't link, hang on a second, let me put that in here. You can see examples of attaching STL files to the end of the gripper. Let's see, where is that? Here we go. Here is our library of example programs here. And there's an example there of attaching a chainsaw STL to the end of the robot, which some of you might realize comes from Shane Whiten's video where he used the chainsaw to carve out the dog. Okay, well, thank you everyone for attending. I really appreciate your time. Feel free to follow up with any questions. Info@tormach.com, addressed to me. or if you remember drogge@tormach.com, that'll get to me also. So thanks everyone, and looking forward to talking to some of you again in the future. Thanks.